Let's talk about homework part 3 of 3, which means next block we're going to actually have a quiz. It's going to focus primarily on the homework of these last three types, and of course a little bit what we've been dealing with in class, but that's reflected in the first two questions. So you should be pretty prepared if you're doing all this homework and you've come in for extra help or asked questions in class and just really generally worked hard. You should be just fine for this quiz. Now, the thing we've added now to this kind of finding the zeros of these functions is going to be that we can actually find all the zeros now, both real or expressed as complex numbers, including imaginary parts. So we don't have to stop anymore when we can't find those real roots really quick anymore. Now we can actually continue the process to find all the roots, which is really now where all the information comes together. So let's take this first equation, for example. If I want to find the roots or zeros of this function, I have to be equal to 0, so I have to do a little moving around first. I'll subtract 4x from both sides and also 4. To move everything to the left-hand side of the equation, which will give me x squared. That looks like negative 2x minus 3 is equal to 0. So now that I have in this form, what I'll have to do is now probably factor, because really it's a choice. You can factor, you can complete the square, you can use quadratic formula, but the thing that's important to note is that it's a degree 2 polynomial, so you should have two roots or roots or zeros in the end. I'm going to take a shot at factoring it first, because if I can factor, that is usually the quickest way to do it. So I'm looking for two numbers that multiply to 3, and then I can somehow combine to make 2. It looks like I should be able to do that with 3 and 1 if I'm really careful and choose, say, a minus 3 and a plus 1. Negative 3 plus 1 makes negative 2 in the middle, so this is good to go. I expected two roots, and I have two factors, and all I have to do now is extract the zeros, which will be the values of x that make those individual binomials equal to 0. So the first one is 3, and the second one should be negative 1. So this is pretty straightforward. No complex roots here, just real parts. Let's move on to b. Same deal. I know I have to make this equal to 0, so I'll do that first. So I have x cubed plus 3x squared minus 6x minus 18. I'm not going to be able to, well, first let me make a note that it's a cubic. So knowing that it's a cubic equation, I expect 3 roots. So my only hope of actually extracting these by hand is to somehow depress this into a quadratic. Given the form, given that there's an x squared and x value, I'll probably have to do some grouping, or at least hope I can do some grouping. And so recall that when I group, I'm looking at this in two distinct parts. I'm taking these first two as like part 1, and these second two terms as part 2, with the hope of extracting a common value out of both. So if I'm looking at the first part, I notice that I have an x squared and x cubed, so I can take an x squared out of both. Back building the distribution problem, that should leave me with an x, because x squared times x is this x cubed, plus 3, because 3 times x squared will give me 3x squared. So now I'll shift focus onto the second part. I'm going to hope to extract this x plus 3 again. So I'm actually going to start with that, because the only way this is going to factor by grouping is if I can take the same binomial out of both, in this case x plus 3. So if I look at what I have, if I choose to take out a negative 6 out of both the negative 6x and negative 18, I should end up with x plus 3 as my value. Now I'm going to reset this, recollect the terms, if you will. So I'm going to collect the x squared minus 6 as a single term, and then the x plus 3 as another factored term. So if I'm extracting my zeros, I should get 1 very quickly. It's the one for the factor x plus 3, which will give me negative 3. Although I do expect 3 total factors, so I should be able to pull out 2 from the second one. Given that it's just an x squared minus 6, I think what I'll do, instead of trying to do like a complete the square or a quadratic formula, try to factor even, I'm just going to set equal to 0 and solve for x. Now this will work in this particular case because I have an even root, even degree. I only have an x squared value here, and so I can take it to solve it just like I would any other equation. So if I want to get rid of the square, I'll of course square root both sides. That'll tell me my x value is going to be plus or minus square root of 6. And square root of 6 is no longer reducible, and so those will be my other two roots, negative square root of 6 and positive square root of 6. Okay, so let's move on to the next set. Here we want to find some more zeros. I have a feeling these are going to produce some more fun results in terms of finding complex roots. But let's go ahead and do this. The first one, I have a cubic equation. but I have all the terms of the cubic, so I'm going to hope to factor this by grouping. Now, it's important to note that all cubics will not factor by grouping easily, although this technique should work every time. So the first one looks like I can pull out two terms. I can pull out a 4x squared, which will leave me with x plus 4. And then moving on to the second one, I already see the x plus 4, so I'm just going to extract a 1, leaving me the x plus 4 as a factor. Rewriting now, degrouping if you will, I'll take the 4x plus 1 to be one of my factors, and I'll take the x plus 4 to be the other. Now this is of course still equal to 0, because this process of factoring simply helps expose the roots a little easier. Now we're going to find the zeros, or the roots. We get 1 for free here, that's going to be a negative 4, but I should have 2 more. Now in the past we'd had to stop here. This is no longer the case. The reason it's no longer the case is because we now have a little bit of knowledge about complex values, complex numbers, and so I should be able to solve this in a variety of ways. Again, I could use a quadratic formula, I could use completing the square. I could try to factor, although I don't think I'll be successful. So I think I'll probably do a more direct, just solving by square root method. So we have 4x squared plus 1 is equal to 0, because we're searching for the value that makes this factor equal to 0. Subtracting 1 from both sides, I should have 4x squared equals negative 1. Dividing both sides by 4, I'll have x squared equals negative 1/4. Now, here's going to be the ultimate problem, because when I go to square root, I'll have to square root a negative value, which may be a little confusing about how to handle, at least it was before. But now we know that we can simply take the square root of 1/4 and separate it from the square root of negative 1. So the square root of 1/4 should be 1/2, because 1/2 times a half should be a square root. And then square root of negative 1 we represent as being the imaginary I. So we have positive or negative 1/2 I, which ultimately are going to be our next two roots. So half I and negative half I are our other two roots. Now these are complex, but that's okay because those are still zeros. Okay, so here notice first we have a quadratic. So we expect two roots, and so either they're both going to be real or they're both going to be imaginary. And now we just have to kind of pick a method to do this. I think the method I want to use is going to be quadratic formula. The reason I'm going to say quadratic formula is because I have coefficients that aren't 1 in front of the x squared, and so it might be just as easy to hop in, extract the a, b's, and c values, and then go to town on the formula. So if you recall, the formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So in just a couple steps, we should know if these roots are going to be real or complex. But let's continue in our formula. So we x equals negative b. Now, one complaint I can lodge, what I've seen in some of the work already, is that we're not using parentheses very well, and that's leading to some very, very bad results. So one thing I'm going to suggest is anytime you substitute a number into a formula, put parentheses around it. It's going to help you maintain the proper number of negatives, and it's not going to lead you to a bad result, as I've seen in some of the quizzes so far. So it's going to be negative b plus or minus the square root. Here we're going to have parentheses come into play again, so we should have b squared minus 4 times ac all over 2a. So that should be 2 times a half. Okay. Continuing the formula, continuing our simplifying root, we should have x equals negative negative 4 should be a plus 4, plus or minus the square root. Now let's try to simplify some things. Now here's precisely why parentheses are important. The mistakes I've seen people make is that they don't write the parentheses. They might type that into their calculator and they get negative 16 in this case. If you're taking negative 4 and then squaring it, that means negative 4 times negative 4. That can't be a negative number because negative times negative is a positive. So that should be a positive 16. Now for the remainder of the result, 4 times half times 12. Well, half of 4 is 2. 2 times 12 is 24. And there's only one negative, so this should be minus 24. All over 2 times a half, which will just be 1, which is great because we can just drop that part of it then. Okay, so continuing our simplifying, we have x equals we have x equals 4 plus or minus the square root of, now 16 minus 24 should be negative 8. all over 1, which again we don't have to account for. Now, this tells us right away that we're going to have two complex roots because we have a negative under a square root. So let's do a little separation here. So we have 4 plus or minus the square root of 8 times the square root of negative 1. So that should be 4 plus or minus. Now, square root of 8 can break down into the square root of, square root of 4 times the square root of 2 times the square root of negative 1. And so our final form should be 4 plus or minus 2 square roots of 2i. Okay, now of course that's going to be two roots because we have the plus version and the minus version, but that's going to be our two roots. So here we have an example of solving where we just have real roots, and then we have an example we just have complex roots. Okay, moving on. To explain to what set of numbers does the domain of the following situation belong, and here's a list of things that we have investigated so far you should be aware of, like real numbers, integer numbers, whole numbers, rational, positive, negative, even, or odds. So a ball is thrown in the air. Its height is tracked as a function of the time it spends in the air. So the function we're looking at is h of t. Height is a function of time. Now it's important to look at it like this because we've identified clearly what our input has to be, which is also called the independent variable. Which is also going to be our x's. So if we're asked to identify the set of numbers which our domain belongs, we're just trying to figure out what can go in for x. In other words, what kind of numbers can go in for time. And so if you think about like ball being thrown into the air, when does the time start for that function? Well, the time has to start just before you actually do the throwing. And so I would say the beginning of your domain has to be 0. Now the ball goes up into the air, it comes back down, and then the function stops at that point. And so there is going to be an ending to that function, and that ending isn't necessarily infinity, so it's going to stop at some value. Okay, so our job is to figure out like what these values represent. Now, beginning at 0, that's pretty much all these sets because 0 belongs to the real numbers. It's an integer. It's not really a whole number. It's a rational number because you can express it as 0 over 1. Positive and negative, those are a little bit kind of in between. It's definitely not negative, but it's not necessarily positive either. It's not necessarily an even number, nor is it an odd number. Now, depending on what resource you look at, it may qualify 0 to be an even number because of patterning, because 1 is odd, 2 is even. So if you go backwards, 0 might be even. And so if you want to include it as being even, that's okay. But so far, we just have these things. Okay? So now what we have to consider is what kind of numbers can we measure time in between the beginning and the end. Is time limited to just like 1, 2, 3, 4 seconds? Or is it limited to, or can it be like those decimal values in between? Certainly it can be decimal values in between, so we eliminate the integers from that. Now, between real numbers and rationals, real numbers can be whole numbers, it can be integers, it can be fractions, decimals, positive, negatives. And then rational numbers have to be expressed as a fraction. And so there are certain things that are eliminated from rationals, like square root values. So if you consider that time never stops, rational wouldn't be a good way to say it either. And so we're really left with our real numbers or even numbers. So again, can time only be measured in like 2, 4, 6, 8, 10? Well, no, it can't be, so we're just looking at real numbers. Now, the other thing I want to bring back, though, is that time cannot be negative. And so we have to kind of consider positive as well. So the only problem with that is like 0 is not really positive nor negative, but we can make that adjustment as we write our actual value. So I would say this belongs to the positive real numbers, and that includes 0. So what I want you to take from this is that when you think about what numbers can be in your domain, you're not limited to a single descriptor or a single set, but you have to put some real thought into what type of numbers these can be, and how you need to modify that set to include things that aren't strictly in that set. So, for example, 0 is not really a positive number, but most of my numbers will be, so I can just add 0 to that set and be okay. Okay. Let's talk about whether or not these are functions. So explain whether or not each of these below mappings represents a function. So recall when we talk about functions, we're talking about one input to one output. And so these mappings are going to help us direct that. Now, the thing to note here is that these mappings are directional, and so they always go from the input to the output. So if I look at the first one, 2 is an input, 2 goes to a single output of 4, so we're still good. 3 is an input, it goes to a single input of 8, so that doesn't violate function. 4 goes to a single output of 8, and 5 goes to a single output of 5, so this is indeed a function. Now I know you're probably saying, well, 3 and 4 go to the same value. That's actually okay, because one x has to determine one y, so there can't be any ambiguity from where x goes to where y goes. And now the thing about that is all the x's can go to a single point, or multiple x's can go to a single point. A good kind of analogy for this would be like a soda machine upstairs. If you pushed like the Powerade button and something other than Powerade came out, if there was some ambiguity with like what you push and what you get, that would be a non-function. But you can have more than one button that gives you Powerade, and that's okay, as long as each of those buttons do indeed give you Powerade. That's what I mean by one input to one output. You push one x, you get one y, even if that y is given by more than one x. A good counterexample would be the second one, because although 4 does map to 7, 5 maps to two values, 5 and -9. This is an explicit violation of your of a function, and so that's why this one's a non-function. So this would be precisely the case I was trying to describe with like the soft drinks, the soda, Powerade. Okay? If you push 5, you could get 2 or you could get 9, and that ambiguity is no good. That's what actually makes it a non-function. Okay? I'm going to stop this right here because it's already gone pretty long. I'll finish up the rest in part 2.